So my name is Arianna Zuanazzi. I am the Open Science and Research Collaboration Specialist at the Childmind Institute. And I'm here with two colleagues, Adam and Nathalia, who are software engineers at the Childmind Institute as well. And we'll be running today a hands-on exploration of child and adolescent mental health with the Healthy Brain Network. We hope that by the end of this workshop, you will be more familiar with what actigraphy is, how to use actigraphy data to investigate mental health, and in general, will be familiar with our data sets and the tools that we share. So here on the left-hand side, you can see the agenda for the next hour. We will be starting by introducing what the Healthy Brain Network is and the data sets that we share and what actigraphy is. Then I'll pass it on to Adam to do a hands-on practice on how to load and plot raw actigraphy data and how to extract features, explore physical activity data, as well as explore the sleep data. And Nathalia will end with an in-depth analysis of what you can do with mental health exploration using actigraphy data, and especially at the group level. We will also share some resources at the end. If you have any questions or run into any issues, you can let us know in the chat. We will monitor the chat and we will try to troubleshoot. But if your question or your issue is not solved immediately, do not worry, because you can still follow along. And then at the end of the workshop, we will share the scripts, the resources, so you can explore the data and the tools at your own pace. I'll get started with introducing what the Childmind Institute is. We are an independent nonprofit that is dedicated to transforming the lives of children and adolescents who struggle with mental health challenges. And we do so through care, education, and science. And the group today, the team, is part of the science department. We mostly focus on neuroscience research, advancing methods, leading and supporting open science and open data initiatives, and advancing applied technology. Why is it important to study mental health? There are millions of people around the world that are struggling with mental health and learning challenges. And globally, this is 1 in 5 children. If we look at the US, 70% of US counties do not have a child and adolescent psychiatrist, which means that due to stigma, misinformation, and the lack of access to care, the average time between the onset of symptoms and the treatment is over 8 years. For this reason, the Childmind Institute in 2015 kickstarted an initiative that is called the Healthy Brain Network, or HBN, which uses a community-referred recruitment model. This means that families and caregivers are encouraged to reach out to HBN and to participate in the study if they have worries about the mental health in their children, and they can receive free evaluations and free recommendation from HBN. Over the years, we have collected over 8,000 data sets from children and adolescents prevalently in New York City, which makes this a very rich data set from the perspective of diagnosis. But we also serve the research community by sharing all of the data that we collect. So the HBN is also an open data sharing initiative for research, education, and innovation. Here, we wanted to show you some of the distributions of the sample that we collect. So on the left-hand side, you can see that our children, so children that participate in the study, go from 5 to 22 years old, with the majority being between 6 and 11 years old. So we really span a large age range. And as I said earlier, this is not a random sample of the population, because participants of HBN reach out if the families or the caregivers have concerns about the mental health in their children, which means that we have over 90% of children that have received 1 or more diagnoses. So on the right-hand side here, you can see the distribution of the diagnosis over the years. Over 70% of children have received a diagnosis for ADHD, 50% of anxiety, 40% of learning disorders, and 15% of autism, language, and depression. Our dataset is not rich only in terms of diagnosis and their age ranges, but also because it's a multimodal dataset, which means that we use different modalities to collect our data. So we use, for instance, questionnaires or computer-based assessment to collect phenotypic data across different domains. We have data from the domain of cognition, language domain, emotional and psychological function, up to substance use and addiction and medical status. We collect neuroimaging data using electroencephalography and eye tracking, magnetic resonance imaging, and we also collect biological samples such as saliva, blood, teeth, and hair samples. But most importantly, for this workshop today, we collect data using behavioral monitoring technology, and today we're going to focus on actigraphy. So what is actigraphy? Actigraphy is a non-invasive method that is used to monitor human activity and sleep over time, so second by second, but as well like across days, weeks, months. And we do so using wristwatch-like device that contains an accelerometer, a light sensor, and a temperature sensor. The kids that participate in the HBN study wear this device day and night up to 30 days. And this is the data that you will see today and you will work with today. And if you're interested in the specs of the watch itself, we have been using two watches, an Actigraph and a GeneActive. So you can look up like these two companies. What is the difference between an actigraphy watch, and a smartwatch? The actigraphy watch is a scientific device. It gives you unprocessed, continuous, high sampling data, and it doesn't have any interactive features, so there is no monitor on this watch, and it also doesn't have any additional features. Whereas the smartwatch is a consumer device. It gives you pre-processed data, for instance, fitness information, steps, heart rate, sleep estimates, and it usually includes notification apps, music, and calls. Why is actigraphy important to study mental health? So there are some mental health conditions such as ADHD, anxiety, and depression that are associated with specific activity patterns or activity levels and sleep patterns and sleep behaviors. So actigraphy provides an objective measure to collect this specific information rather than self-report, which could be, for instance, asking specific questions to the participant, which is important in the case of the study that includes children. It also provides continuous real-world data that picks up on day-to-day variability, and it does so in natural environments, for instance, at school or at home, rather than in an environment such as a lab. It also can be paired with other data that is collected, for instance, through ecological and momentary assessment, which is real-time information about the behavior and the mood of the child, for instance. Overall, actigraphy really provides detailed information about children's behavior. For instance, does the activity pattern show low or hyperactive features? Is it irregular? Is it regular? Is the sleep, how long does the sleep last? Is it interrupting overnight? So these are all information that we can get through actigraphy. And so it represents a relatively low cost and scalable data that can be integrated with other measures and that can support diagnosis. So I hope that this brief introduction made you a bit more aware about what actigraphy is and is going to be useful for the next step, which is the hands-on part of this workshop. And so I'll pass it on to Adam to lead this part. Thank you.
Great. Thanks, Arianna. Just before we jump into the notebook that we're going to do the hands-on part, I want to bring up a few key terms about what we'll be talking about. So the data set today, we're looking at 2 participants from the HBN data set. They are both have a ADHD diagnosis. The data was collected during the fall, but we have 2 relatively distinct age groups. So a 5-year-old girl and a 14-year-old boy. And for today's exercise, we've truncated the data to 1 week. So if we try to load and process the full month of data, we'd be sitting here maybe waiting for a bit of large chunks of data. So it might take a while. So we truncated it to 1 week. Now, just to go over a few key definitions again before we start, the accelerometer is collecting triaxial data. So in 3 planes, the XYZ plane, if we imagine, where you could pretend the Z-axis is towards the Earth's core, and we're getting measures in G-forces, so relative to Earth's gravity. You'll hear me mention probably the word ENMO, or the acronym ENMO, which stands for Euclidean norm -1. This is a measure of movement, where -1 means that if you're stationary, you'd be experiencing 1 G-force approximately on Earth. So ENMO -1 would be 1 - 1 would give you 0. So you can imagine the number 0 would be stationary, and large numbers means you're moving pretty vigorously. And I'll also mention something called angle Z. This is the angle of the wristwatch relative to the XY plane. So you could imagine a 2D plane. The angle of the watch relative to that plane is something I will call angle Z. And this is used primarily for us anyway in sleep detection. So now I'm going to hop into that notebook. It's been shared in the chat. This has been mostly pre-filled, so you can just follow along via the screen, or you can try and run each cell by yourself. So Google Colab provides, you can imagine, for those unfamiliar with it, it's a Jupyter notebook. It's like a playground or a sandbox where you can test out different scripts of code that you've been working. You can even play with Gemini if you want. You can create a little table of contents for a presentation, but it's a nice open source, free I think there's a paid version. You even have some GPU compute power. And what we're going to do is we're going to look at two software packages we've developed at CMI. They're called RiskPy and Not Sleepy. RiskPy is our toolbox to process raw actigraphy data. So those two watches that Arianna mentioned, if we get the data from them, we can read it and process it into a format that we can analyze. So CSV or a variable in our Python environment. And Not Sleepy is a toolbox we've developed for nocturnal sleep analysis. Okay, and for those unfamiliar, an easy way to install packages, especially in Python, is using pip, which is the default Python package manager. So you can just write pip install RiskPy, you run this cell, and you'll see that it will collect some downloads and requirements and should install successfully. It may ask you if it's the first time installing RiskPy on your environment. It may ask you to restart the session. I have a new session. So I'm doing it live with you guys. Then you can install the next software package, Not Sleepy. Same thing will happen. And then we've also, while that's running, I'll just be speaking. We've also provided the data accessible to you guys in these S3 buckets. And you could run this cell after you install, unfortunately, another package. This is just for grabbing the data. Once that's run, the files are approximately, I believe, 700 and 300 megabytes. So if you're on a slow internet connection, it may take a while, but it shouldn't be too bad in the modern day. All right. And there'll be a little message here you can see. So downloading, and once it's actually been saved, just put a little blurb saying save that. Shouldn't take too long. Yeah. And once they've actually been downloaded, you'll see it a pop-up here. So you'll see Open Data Week participant 5-year-old, Open Data Week participant 14-year-old, and they're CSVs. Normally we have the data from the watches in a proprietary format, but for the Open Data Week, we've been sharing them as CSVs. But we can still use our software tools to read them and process them. So the first thing we're going to do is we're going to import the reader from RiskPy. And we're going to define a path to where our data is. And then we're just going to do something as simple as just read watch data and the data path. This will take, remember, this is free compute from Google. It should run faster if you're ever exporting this notebook to run it locally in your VS Code or some other IDE or you have. But on Google Colab, it might take about, on the cloud or their free compute, might take about a minute. While that's loading, you can just see that we've developed this package so that it plays nicely with IDEs. So you can actually read, what does the read watch data function do? Oh, it was fast today, only 30 seconds. Like I said, it depends on who else is using the free resources at Google. You can see what it does. So a description of read watch data is, what the required arguments would be, what it gives you back, and if there's any errors that raise, what they look like. So now we can actually inspect this object. So read watch data has returned, you see here, a watch data object. So if I just write this variable name here, raw data 5-year-old, I can see I have a watch data object, and within it, there are different attributes. So there's an acceleration. We have lux for luminosity. There's battery, capacitive sensor, temperature, idle sleep mode flag, which is something I don't really want to get into right now. But if someone's very curious, you can go look up actigraph idle sleep mode and you'll have a fun day. And you can also see other information about the size of the data that's been loaded. Each attribute can also be accessed pretty easily by just writing, it didn't matter which one, but you can access it by just doing dot and then the attribute name. So if I just want to look at acceleration in particular, you can see measurement has the 3 axes, as I mentioned earlier, X, Y, Z, and then associated timestamps for each recording. And you can see the precision here is 30 hertz. The next thing I want to do is, okay, now that we've read the data, maybe we should take a look at it. This is, as you saw here, 20 million samples. So maybe we'll just look at the first 2 million. You can use For those unfamiliar, with plotting in Python, commonly used package and pretty straightforward is matplotlib. You can see it's just say a number of points, make a plot, X column, Y column, put a label, and show. So you can run this cell. Once again, should be relatively quick. It is 2 million points. You can obviously plot fewer if you would like. So these are the 3 axes of the accelerometer data, the raw data we've recorded unprocessed for about the first 2 million points, which is about, I think, what's this, 1, 2, 3, about 8 hours of data. So you can see periods of activity and then periods, as you can see, midnight, where there's much less activity, and that's probably sleep. Okay, that's just the raw data, but can we do anything interesting with RISC-Py to process the data, to get some interesting features like the NMO, angle Z, sleep, physical activity metrics? And to do that, we have something called an orchestrator, which is like the main function. And within that orchestrator, once again, I'm just going to press play. This can take locally anywhere from around 10 seconds, but running it here may take about 30 seconds to a minute. It's very simple. You can just write orchestrator.run, the path that you want to analyze, which is the same as we had before. And then you can define an output path. The output, as you can see here, is in a nice, easily readable format. It's in a CSV, so something that you don't even need to use any fancy code to analyze if you're comfortable with Excel, or you can import the CSV into other coding environments or processing environments. What I want to show is that I'm running the default, so just an input and an output. But if I hover over run, once again, you can see there are actually quite a few parameters that if you have an idea of what type of processing you want to do and you want to specify what those parameters are, you can set them. So I could set different thresholds. This is for the physical activity levels. So if you are wanting to threshold the physical activity between sedentary, light activity, moderate activity, vigorous activity, you can change these thresholds. Right now, it's set to default values that we are pulled from literature. There's different methods you can use to calibrate the data. You can define an epoch length, which is the temporal resolution of the output file, right? It defaults to 5 seconds, but it could be any value you like. We have different activity metrics. So right now it's NMO, which I mentioned earlier, which is the default, but you can choose any of these 4 or any combination. It can be, doesn't have to be 1, it could be more than 1. These are, for those familiar with actigraphy data, they are different ways of calculating physical activity. They are all highly correlated with each other, and they all highly correlate to METs, a form of energy expenditure. There's different algorithms to detect non-wear, and then there's some other specifics. So I'll also run it for the 5-year-old. And while that's running, I'll just go back to our data, and you can see the results will appear here as well for you. And you can just inspect these pretty easily. You can see there's also a JSON. So even though I said it creates a CSV, it also creates just a text, a dictionary here of what the processing parameters were when you ran RISC-Py. So you can say what time of day it was ran. You can see the version number, which is always good in case there's ever updates and you want to compare why your results might be different from time to time or person to person. And the other ones I had mentioned in that run file. So the thresholds, the calibrator, epoch length, activity metric, etc. And there's also the CSV, which we could preview here. You can see the output is nice tabular data, is just columns of these different output metrics. So we have a column for NMO, we have a column for the physical activity levels. So as I mentioned, inactive, light activity, moderate activity, vigorous activity. There's a time column, angle Z, which we had spoken about briefly before, and I'll come back to later. There's a non-wear status, so whether we detect that the watch is being worn or not. And then we have 3 columns related to sleep. The primary one is sleep status. It's set to a Boolean, so true or false. False being you're awake, sleep is false, or true being you're asleep. Then we have these 2 columns. They're more specific for those who are interested in sleep research. Specifically, they stand for sustained inactivity bout and the sleep period time. For today's workshop, we will ignore it. We just know that they are accessible for other sleep computations. Okay, so the results for the 5-year-old are also ready. Now, besides the CSV and the JSON, we actually can look at it in our environment here. And same like before, it's created an object. This object is called the orchestrator results object. And within that object, you can see there's attributes for the physical activity metric, attributes for angle Z, physical activity levels, non-aware status, sleep status, and then the two other sustained inactivity bout, sleep period time, and also the processing parameters. We can also go on to visualizing results. So same like we did before with the visualization of the raw data, but this time I'm going to show you guys another option for plotting in case anyone's unfamiliar. This is called Plotly. It's very nice because the plots are interactive. It is a bit heavier, so it may take more compute. The caveat is don't go trying to pass 40 million rows of data to Plotly. It will probably crash your computer, especially with RAM being so expensive these days. So what I've plotted here is on the y-axis, the Euclidean norm -1, NMO, the measure of physical activity, where, as we recall, when it's close to 0, that represents periods where you're stationary or idle. And on the x-axis, it's time. And in red, I have the NMO activity levels for the 5-year-old, and in blue, the 14-year-old. And as I mentioned, the Plotly plots, that's a bit wordy, are nice because you can zoom in, you can easily pan to different areas, and you can make observations. You notice the 14-year-old's a bit more active later at night. That makes sense. The 5-year-old in general seems to have higher peaks. Maybe they're running around. I have a 4-year-old. They're a little crazy. Yes, that's something you can do, plotting the physical activity metrics. Another thing we could look into is sleep status. And one thing I'd like to compare this to is the angle Z, the angle of the watch relative to the XY plane as mentioned. So what I'm doing here actually is I'm using two y-axes. So sleep status going from false or true or 0 to 1. And on the secondary y-axis, angle Z going from -90 to +90. And what you'll notice here is that our sleep window correlates really highly to these changes in angle Z, where the rate of change is at a much lower frequency, right? There are far fewer high frequency changes in angle Z during sleep, which would make sense. We're probably not moving so much, but there are still some moving around. And one thing that Arianna had alluded to is that how does movement look like depending on your potential diagnosis? Does someone with ADHD move more at night, especially during sleep? One interesting point of research is looking at what this movement looks like during sleep for someone without a diagnosis and someone with ADHD. This is something that could be interesting from a research standpoint. And then the other plot I have for you guys is actually just the 5-year-old and the 14-year-old sleep patterns compared to each other. And I thought two interesting nights are these two right here, or maybe not interesting, but things you would maybe expect, right? The 5-year-old goes to sleep earlier, wakes up a bit later, and the 14-year-old's going to bed pretty late, waking up pretty early. Or in this case, they both wake up pretty early, and they're both 14-year-olds still going to bed much later. So you can pan through, you can zoom, reset the scale, etc. Now, one other thing we could look at is we can say, all right, let's look at the non-aware data. And then you might notice, oh, that's interesting. It seems almost every night, almost except April 8th, at the same time, there's this short period of non-aware. As a researcher or data scientist, this would be interesting. So you can hypothesize, okay, maybe they're taking a bath before bed every night, and the child took the watch off. Let's compare the non-aware with the sleep status. We're going to plot both traces at the same time. And we'll zoom into a couple of nights. And you can see that right before sleep, there's this period of non-aware for 2 nights in a row. Now, it's possible that the participant took the watch off, had a bath, put it back on right away before bed. That's one possibility. But is there some other possibility? Let's look at that angle Z metric again. So we're going to do the same plot. We're going to have a secondary y-axis for angle Z. We're going to plot sleep status and non-aware on the other one and compare the two, or 3 in this case. Zoom in again to one night. what you can see is right here, right before sleep, or what we detect as sleep, there's this 45 minutes to an hour of very still, right? This is the angle Z plot in green. And we have non-wear and sleep both being 0 to 1 or false to true. And the issue is, right, we're as good as these actigraphy data and useful it could be, it's still only using one feature at the moment to detect sleep. So we're only checking changes in this wrist angle, and periods that are very flat where there's no change look like non-wear, because as you can see for the rest of the night with sleep, there's some low frequency changes happening throughout, whereas this extremely flat part here looks more like non-wear. Now, maybe it is non-wear, because that does look a little too perfect. You can see the value is exactly the same. Or maybe they're just a very still sleeper. And this is the best part of research or engineering, is like, all right, we're doing pretty good, but is there a way that we could get better if we had the capacitive sensor or temperature from the watch? And some watches do have it. Unfortunately for this study, this older study, we weren't using the watches that had all three features. You can improve your algorithm by making use of more features to iron out whether this is actually non-wear or if it was just someone sleeping very still. I have here run RISC-PI in the terminal. I'm just going to do this, open it up real quickly. But you could open up a terminal here. There's a little terminal button. And just to show you, you can run RISC-PI from here. I'm just going to show you what our help. I'm going to move this pane to the bottom because it looks nicer at the bottom. But if you're more comfortable running things from the command line, there is support in RISC-PI to just run RISC-PI from the command line. And you can write RISC-PI help. It'll show you all the same parameters, processing parameters as we have with the Python interface at the orchestrator run level, but you could do it from the command line. And this looks really pretty, so I thought I would show you because I like it a lot. All right, getting to Nox Sleepy, our second toolbox. This is used for analyzing the sleep information. So we're going to import this. And then we're just going to compute sleep metrics for the 14-year-old. And this is same thing. It's a nice, easy call. It's just compute sleep metrics, data path, and the time zone the data was collected in. This is important for daylight savings time. I've worked on this, and I can say that time zones are not fun, but we are hopefully handling the daylight savings time correctly as long as you provide the correct information. And there's, like I said, there's an explanation here and all the documentation on how exactly we are handling daylight saving times changes. Are we using the anatomical clock or the wall clock? And that is actually feature dependent. So you can run it with just like this, just with an input and a file name and a time zone, or just like before, you can have specific parameters that you would like to pass. You can run this. Nox Sleepy is very fast. That's basically instantaneous. I'm now realizing there is a cell missing right here. I forgot to include for the 5-year-olds. So just in case you want to see what it would look like if I typed it in. There we go. So we'll also compute these for the 5-year-old participant. And as before, let me reload this folder. You'll see some files that will appear here. I open up this one right here. Sleep metrics. The sleep metrics are provided in a JSON, which is just a text file. And you can see we export the night dates. So which nights are being analyzed, the number relative to the data collection day number, and then various sleep metrics. These are per night metrics. So the sleep duration in minutes, the time in bed in minutes, WASO, which stands for wake after sleep onset. So how much time you actually spent awake after sleep was first detected, sleep efficiency, the number of awakenings per night, so on, and then also summary statistics. Besides from that file name, you can also access that information directly here in your environment. You just write whatever you define as your variable, and you can access the different attributes. So if I wanted sleep efficiency, as we looked at there, I press run, you'll see the sleep efficiency as a percentage per night. The last thing I want to show you guys today was how can we use the process data, so the results CSV, to look at physical activity metrics. So I'm going to use Polars, which is a super fast equivalent to Pandas. What is Pandas? It's a way to look at tabular data. So if you have data frames or matching tables, if you will, how can you look at that information in those tables quickly, access by column name, do some math on those columns, different processing. I'm going to read the CSV, which is the results we computed earlier. I'm going to filter them by removing, so this is just a not in Python, removing the non-wear status and the sleep status. So whenever someone is asleep or not wearing the watch, we're going to remove all of that information, and we'll call it filtered data. And then I'm going to compute daily metrics for each participant. And this is just showing you some of the fun stuff you can come up with when you're using these different packages. So Polars is really good at chaining things together. So you can see here, I'm going to group by the day of this filtered data. I'm going to group by the day, and then I'm going to perform all of this. And at the end, I'm going to sort by date. And what am I going to perform? AGG stands for aggregate. So you're going to aggregate all this functionality. I'm going to grab the physical activity level. I'm going to find when it's inactive, equal to inactive. And I'm going to take the sum of all of those. And then I'm going to multiply by 5/60, which is just the temporal resolution in minutes, right? The temporal resolution is 5 seconds, 60 seconds per minute. And then I'm going to call that sedentary duration. I'm going to repeat the same thing for light, moderate, and vigorous. I'm going to assign them different names in the alias. Then I'm also going to check when it's in M or V, so in moderate or vigorous, and take that sum. This is called NVPA, so moderate and vigorous physical activity, which is often used as a metric for looking at activity in general. And then I'm also going to take something called total activity count, which is just the sum of the animal value. And then there's a log-based version as well called TLAC. I'll run this, and what's nice about Polars, you can see super fast. It's instant. And lastly, before I go over time, is a plot comparing these physical activity metrics. On the first bar plots, I'm going to compare light, moderate, and vigorous duration in minutes. Light duration, moderate, and vigorous. This looks a little stretched right now, unfortunately. And I'm comparing the 5-year-old and 14-year-olds per day. So this is y-axis, duration in minutes, light duration, light activity, moderate activity, and vigorous activity. You can see far more vigorous activity for the 5-year-olds. And then in the secondary plot, you can see like what is the total sum per day. So on average, the 5-year-old is far more active than the 14-year-old. And that will take us to the end of this workshop. I hope I didn't go too fast for everyone. I'll get back to the chat as soon as I stop my screen share. And then if there's any questions, I believe there should be links to the repos for both of these toolboxes, so you can communicate directly through GitHub as well. All right, thanks, everyone.
Okay, I'm Nathalia. I'm going to lead the third part of our workshop. Basically, I think you might be thinking, okay, I finished my data collection, or I got the data from collaborators. I processed all the data on RISPy, and I got all the sleep information that Adam just showed after processing the RISPy output into Noctis Sleepy. So what is the next step? Am I done with my actigraphy analysis? Can I do actigraphy analysis after data processing? Still no, just wait a little bit longer. First of all, before all the processing steps, we need to perform a quality control step. And why is this important? Because the processed data has a lot of information of when the device was not worn. And Adam showed to us that RISPy generates that output for us, and then we can clean the data to not consider the times when the kid or the participant was not wearing the watch. Most of the data processing tools that we have available right now, they rely on a sleep diary or on prediction algorithms to detect sleep patterns, sleep and wake up times. As RISPy is part of a prediction algorithm, and a sleep diary is a tool that we can ask the participants or the parents to just write it down when the kid went to bed, when the kid woke up, when the kid took their watch off. And we can include all that information into our data and then perform
the quality control step. And also quality control is important because with them, we can detect inconsistencies with the data, such as, for example, flagging participants or days that don't meet a minimum wear time per. The watches that we are using here, the Actigraph and Genactive, they have proprietary tools. However, they are expensive and they are not sold with the devices. We need to buy these tools. And with these tools, we can also process the actigraphy data and we can perform manual annotations with these tools. If we don't have the tool, we have only RISPy. We say, okay, I'm not going to spend money because I have a nice free tool that I can use, which is RISPy. Okay, I ran RISPy, so now what do I need to do? We need to visualize each one of the days. We need to plot each one of the days. And since this is a prediction algorithm, it can detect the wrong sleep or wake up time. That's why manual annotation is important. The process is tedious, is time consuming, and is prone to errors. Imagine you need to open the data and you need to type on a CSV the exact time the kid went to bed and the exact time the kid woke up. You can, just by typing, instead of typing 10 p.m., you can type 11 p.m. And then you're detecting 1 hour wrong your data. Thinking of that, we here at TMI, we created the Active Sleep Tracker, which is a web app tool to annotate actigraphy data. This tool is available on GitHub. We have the link here on this presentation, and now I'm going to show to you the interface of that. After you install the tool and run, you can open your, for example, Google and type the URL that the tool will give it to you when you're running. In this case, since it's running locally, it's 000. After you type it, you can select, the tool will appear on the screen, and then you can select the data that you want to analyze. Once you select the data, you can see here the time series, the arm movement, the ENMO, and the angle Z. And you can see in the red rectangle, the red shade here, the predictions from the sleep, from RISPy. And you can easily, by using the slider here on the top, you can easily go through each one of the days. It's just take a few seconds to load. And then see, okay, is this prediction correct? Yes, it looks correct. And here we have some things that you can also do with your data. For example, here on day 3, we can see that around 2:30, from 2:30 to 3:15, the kid, it seems like a sleep pattern here, right? So probably the kid took a nap. What you can do with this tool, you can add a new slider. Add a new slider, and you can manually annotate the new sleep period, the nap time. Once you do this, the tool will automatically generate a CSV file, say on this day, April 4th, between 2:23 and 3:15, the kid was sleeping. Okay, you're navigating through the days, and let's say that you found a day that you need to adjust the sleep window. So, for example, on April 9th, as Adam showed to us and explained, we have this period here around 4 hours where the kid is really still. Looks suspicious, right? Looks like nowhere. So what you can do, okay, this is not right. I need to adjust the wake up time. What do you need to do is just slide the slider to the left until the desired time. And as you do this, the tool will also automatically generate a CSV file with the new annotation, the one that you just moved in here, you just updated. And on the bottom here, you can see the prediction times. So for example, RISPy predicted a wake-up time at 10:57 a.m., and we fix that to 5:52 a.m. And the second time here is the one that is being inputted into the CSV file. After that, we have quality control. We have all the files that we need. We know exactly when the kid was wearing the watch, exactly the wake times, the sleep times, what kind of analysis we can do. Arianna mentioned early in the presentation that our HBN dataset, the Healthy Brain Network dataset, the majority of the participants were diagnosed with ADHD. And it's the same, ADHD is the majority of the diagnosis also for our actigraphy dataset. And the kids, they might have more than one diagnosis. And this is what this upset plot here is showing to us. It's showing the interactions between the diagnosis. So this is something that you can also consider when you're doing data analysis. Do I want to consider only kids with an ADHD diagnosis? Do I want to consider only kids without any kind of diagnosis? Or I can consider, for example, ADHD and autism diagnosis. If you want to get participants with these two diagnoses, we have 130 kids with both diagnoses. Some other information that are also available on our website that might be important for you to consider on your analysis. Age ranges, because you want to only, for example, run a study, run an analysis, considering only kids between 7 and 10 years. We don't want to get 15 years plus. We don't want to get adolescents, just the younger kids. And also something that a lot of people don't consider is enrollment season. In which part of the year the watch was worn? Because why is that important? You don't want to put in the same bucket a kid during the winter that wearing the watch during the winter, getting cozy inside their house, with the data with a kid in the middle of the summer on summer camp. Their physical activity during the day will be really different. And this is because of the season and not only related because of the participant and the diagnosis. Another feature that is important for us to consider is the compliance with the actigraphy dataset. Here on this plot, we have on the x-axis the minimum number of valid days, and on the y-axis, we have the percentage of subjects with actigraphy data. For example, if I want to get the data from participants that wore the watch for 8 days, what is the percentage of time that I want to include in my study for these 8 days? Is it the kids wearing the watch 24 hours for 8 days? Or kids wearing the watch for 90% of the time, 50% of the time, 50% of the day? If you want to consider only kids with 100% wearing the watch 100% of the day, you can have around 45% of our data set. 8 days, 100%, 24 hours a day. If you don't want to be that strict and say, okay, if I consider only 12 hours of data because I just want to consider sleep analysis, you will have around 70% of our data set with that characteristic. You have all the nice features that were generated by RISPI and NoctiSleepy. What else you can do analysis with? You can look at sleep onset, wake-up times, and also sleep duration. You can categorize that by all of the days here on the top row. You can consider only the weekdays. You can compare that with the weekends here on the bottom row. You can also split the data set into age quartiles to see the differences in sleep onset and wake up between age quartiles. So here, for example, is really nice and expected that the older kids here represented in red, they tend to go to bed a little bit later than the younger kids. But on average, and especially on the weekdays, they all wake up at the same time because of school. And it makes sense. So this is something interesting about the data set, and it's another feature that you can get from the data. And now going to the animal part, which represents the activity trajectory during the day, how much the participant was moving during the day. Here I'm showing plots, the average plots over a 25-hour period of time. So we can do also split the data into weekdays, and then here on the panel B, we can see then on weekdays, on days of the weekdays, yeah, exactly, weekdays, the kids, they have more movement here around 8 a.m. and over the weekends, they tend to move less at the same time. Again, is school happening at the time? We can also plot by the trajectories, the ENMO trajectories, the average by age category. And as expected, kids, the older kids here represented now in purple, they tend to move less during the day than all the other age ranges. And lastly, Adam mentioned something that we can, based on animal, we can calculate the percentage of the time that the kid stayed in sedentary, light, moderate, and vigorous activity. And this is also something important to consider during your analysis. And this is also an important feature to show and to plot. Here we can see, as we probably expect, that older kids in purple, they tend to spend more time in sedentary activities compared to the younger kids. And since they stay more time on sedentary activity, they tend to spend less time in vigorous activity. And on our HBN data set, girls, they tend to move less than the boys. So we are really happy to be here and to show you and introduce you to our Healthy Brain Network multimodal data set. Today, we learned why actigraphy is an important data set, and especially because we can use this data, actigraphy data, and it's important to integrate with other multimodal analysis methods, is because some mental health conditions, they are associated with a specific activity levels and sleep patterns. And actigraphy is an easy way to get sleep times and sleep patterns. We saw an introduction to data processing with RISPi and NoctiSleepy. And just to be clear here and to say one more time, RISPi implements a prediction algorithm to detect sleep. And since it is a prediction algorithm, it can make mistakes. So quality control assessment of your data using active sleep tracker, for example, is really important to ensure data quality. We saw some in-depth analysis of features that are important that you can extract from your actigraphy data set and from the Healthy Brain Network data set, and how you can integrate this information together. And we are happy to share that the actigraphy data will be publicly available by summer.
Thank you, Nathalia, and thank you, Adam. We just want to conclude by saying thank you for joining. All of the resources that we have shared, including the slides, the notebook, the analysis tools, is available in these links. And I will also put again the links in the chat. We have also other data sets that you can find out about in this link to the HBN website. And I think we addressed all of the questions in the chat, but if you have more questions, you can contact us as CMI Data Usage at childmind.org. And thank you, Oliver, OTI, Beta NYC, and thank you, Data Through Design, for this fantastic week. And we are really happy that you're here, and thank you for joining.